The question is, for the system 2AD2 gas giving 2AD gas plus D2 gas, if the degree of dissociation is X, which is small compared with unity at temperature T, then the expression for X, that is degree of dissociation, in terms of equilibrium constant Kp and total pressure of P is what? So we are given the system, that is 2 of AD2, it's a gaseous system, to give 2 of AD gas plus D2 gas. Since the degree of dissociation is X, let us assume initially there is only 1 mole of AD2 and no moles of AD, no moles of gas D at time t is equal to 0, that is initially in the closed container. Since X is the degree of dissociation, what do you mean by that? X moles of AD2 undergo dissociation per mole. Out of 1 mole, what moles of AD2 is undergoing dissociation? That is called degree of dissociation. Therefore, we can write 1 minus X. That is, out of 1 mole, X moles dissociated. And from the stoichiometric form, every 2 moles of this AD2 will give 2 moles of this. So X moles being dissociated, X moles of AD we get. And here 2 moles of AD2 is giving only 1 mole of D2. Therefore, X moles will give half of it, X by 2. So these are equilibrium moles at time of T equilibrium. Since degree of dissociation is expressed in terms of Kp, equilibrium constant in terms of partial pressures, we need to find the mole fractions of all this. So therefore, the total number of moles Nt at equilibrium is 1 minus X plus X by 2. That comes out to be 1 plus X by 2. These are the total moles at equilibrium. Number of moles of AD2 1 minus X by total number of moles 1 plus X by 2. Therefore, partial pressure of AD2 is what? Mole fraction of it, that is 1 minus X by 1 plus X by 2 into total pressure. So this is partial pressure of AD2. Similarly, partial pressure of AD, what is the mole fraction of it? X by 1 plus X by 2 into P. Similarly, for D2, partial pressure can be written as X by 2 by 1 plus X by 2 into total pressure P. So these are the partial pressures. Now let us substitute in the equilibrium constant expression Kp. For equilibrium constant expression Kp, AD whole to the power of 2 into D2 by AD2 whole to the power of 2. Therefore, Kp is equal to the partial pressure of AD to the power of 2 into partial pressure of D2 by partial pressure of AD2 to the power of 2. This is the equilibrium constant expression. Let us substitute Kp is equal to P of AD2. So we have X by 1 plus X by 2 into P total pressure whole to the power of 2 into partial pressure of D2 is how much? X by 2 into 1 plus X by 2 into P whole to the power of 1. That is, power of 1 is nothing but that only. Then divided by P of AD2 whole to the power of 2. So it is 1 minus X by 1 plus X by 2 into P whole to the power of 2. And remember that it is given X is too small compared to 1. Therefore, we can make an assumption that 1 minus X is nothing but 1. 1 plus X by 2 is nothing but 1. So, making use of this, that X is too small comparing to 1, we can write it as Kp is equal to X into P to the power of 2, that is X square P square by 1 plus X by 2 will become 1 because X by 2 is too small comparing to 1 into Xp by 2 into 1 plus X by 2 can be written as 1 itself. And here if you can observe 1 minus X is 1, 1 plus X by 2 is 1. So therefore simply P square. So this P square, this V square get cancelled. X square into X cube into P by 2 is equal to Kp. Therefore X is equal to what? 2 Kp by P under cube root, which can be written as 2 Kp by P whole to the power of 1 by 3. So thus the degree of dissociation X in terms of Kp and P can be written as 2kp by p whole to the power of 1 by 3. Now let's go for the answers. So first option itself we have x is equal to 2kp by p whole to the power of 1 by 3. Therefore A is the right option. Here kp by 2p whole to the power of 1 by 3 is equal to x is given 2kp by p. Therefore this is wrong. Here whole to the power of minus 1 by 3 is there. Hence is wrong. Here whole to the power of 1 by 3 is there, but kp by p 2 is not there here with respect to kp. Therefore this is also wrong.